So, next we will start with the basic computer organization part. So, all the microprocessors and microcontrollers that we will be discussing. So, they will be part of this any computer system. So, we will start by looking into the computer system from the outside and the at the major component level, and then slowly go inside and talk about how these processors are organized and how are they designed, how are they used, etc. So, in any computer system, so you can find some components like this. The basic component that we have, one is the central processing unit or the CPU, and we have got two major components which are apart from the CPU. One is the memory, one component is the memory, and the other component that we have are the peripherals. The peripherals. Now, so the memory, so that is actually used for storing the program that the processor will execute, and the peripherals, so they are used for giving input and giving input to the system or taking output from the system. So, when the user is interacting with the system, so the user interacts via these peripherals, and the program that the processor is executing is stored in the memory. And the processor is actually the central processing unit or CPU that we have talked about. Now, the connection between the CPU, peripheral and memory, so this is often done by means of some bus. Okay, so, normally we have got a number of buses. The first bus that we talk about, so is known as the address bus, we call it the A bus. There is another bus which is the data bus or D bus, and there is another bus which we call the control bus or the C bus. Okay. So, this address bus is actually giving address to the memory, that is memory is a collection of set of locations where the values are stored. So, whenever we are talking about memory, so we have to tell which location we want to access. So, if I consider memory as a container like this, so it has got several slots in it. So, I have to tell which slot am I referring to. So, that is actually given in the address bus. So, address bus, the processor, it will give the address on the address bus. The processor will give the address on the address bus. Then we have got this data bus and this control bus. So, on the data bus, the data will be available. So, either the processor as part of its execution will try to write something onto the memory, or it will try to read something from the memory, and same is true for the I/O. The processor may try to read something from the peripheral device, or it may try to write onto the peripheral device. So, that way, so this data bus, so it can contain the data coming from the processor, or it can contain the data coming from the peripheral. So, this address bus you can say, so this is the direction is from the processor towards the memory or peripheral, whereas this data bus that we have. So, this data bus is bidirectional, because I can have this data transferred from the processor to the memory or from memory to the processor. And this control bus, so control bus is again the collection of lines that sends control signals to the memory and control signals to the processor, to the peripheral. So, these control lines are also coming to the coming from the CPU or the processor, where it will give the control signals to these modules. So, this way conceptually I can say that if this is my CPU and this is the memory, then there are three buses. One is called the address bus, one is called the address bus, one is called the data bus, one is called this data bus, and the other is the control bus. So, this address, data and control, out of that this address is unidirectional from the processor towards the memory, or we can have the data bus which is bidirectional. So, it can carry data in both the ways, from processor to memory or memory to processor, and we have got the control bus. Now, so this how big a memory the processor can handle. So, that is given by the size of the address bus. So, if you look into the initial systems or initial processors that were designed, the number of bits allocated for this address bus was less, but as we are progressing. So, the size of this address bus is also increasing significantly, and nowadays it is common to have 64 bit address bus or even higher than that. Now, the question is, if I have got a k bit address bus, using this k bit address bus I can differentiate between 2 power k memory locations. So, just having the processor capability to handle k bit address is not sufficient to tell that the memory size is that much, because this memory that we are putting into the system. So, this should also have 2 power k locations in it, and you can understand that if k equal to 64, then this 2 power 64 is a huge number. So, it is very much difficult to have that much of physical memory in the system. So, if you are thinking about a low end system which which may not have that much memory, but the processor has got so many address bits, then how can I do this interfacing, like how can I connect a memory that has got less number of locations to a processor that has got more number of address lines. So, this is done by the set of topic which is known as the memory interfacing problem. So, we will start with an example. Suppose I have got a processor which is a CPU, where the address bus is 16 bit. So, it can go for 2 power 16 locations, that is 64 k locations, and the data bus from the processor, it happens to be 8 bit. Fine. The data bus is 8 bit, that is once the processor accesses a location. So, it is expecting 8 bit of data from there, but the memory chips that we have, so they are of size 2 kilo into 4 bit. What I mean is that, so this if you look into a particular memory chip, so it has got 2 k locations in it, that is 2 into 1024, the 2048 locations are there, and individual locations. So, they are consisting of 4 bits. So, one thing is obvious, that if I have to cater to a data bus of 8 bit, then I need 2 such parallel modules. So, one module will not be sufficient for giving 8 bit of data. That is one side I have solved the problem from 4 bit chip. So, I have got 8 bit data bus created, 8 bit bus created. But what about the other side, that is I have got this 64 k memory, the 64 k address locations addressable by the CPU, but my memory may not be that much. Suppose I have got say less number of chips, suppose I have got only say 8 such chips, only 8 such memory chips are available. So, I have to so what is the total size? So, I have got 16 k location and each of 4 bit. Okay. That is in terms of bytes, we can say it is 8 kilobyte of memory that I am trying to interface with the system. 8 kilobyte, but the CPU has the capacity to address 64 kilobyte, but my system that I am developing, so it will have only 8 kilobyte of memory. So, it does not, maybe my system does not require more memory. So, I will be sufficient with a satisfied with 8 kilobyte of memory, because putting more memory means the cost of the system will be high. So, I do not want that. Now, how to do this interfacing? Okay. So, what we have is if we take this as the CPU, okay, from the CPU we have got the address and data buses coming out. Now, I have got 4 bit memory chips. So, I take those chips here. Okay. So, these are those 4 bit 2k by 4 bit chips. Okay. I take all the 8 chips in this fashion. Now, this memory is 2K. So, what is the number of address lines that we need? So, for 2K I need 11 bit of address, because 2 power 11 is 2048. So, this individual memory chips, so they have got the address lines which are 11 bit. So, from the CPU, if I say that I have got the address lines A0 to A10, so this A0 to A10 I connect to all these chips, their address lines. Fine. So, it is connected to, similarly it also goes to the next row and it is connected to all of them address lines. But I need to define, like any value of A0 to A10 coming, so it will be selecting some location in each of these chips. And for the data bus part, I can do it very simply, because this data bus I have got two parts in it. So, 3 bit 4 bit 4 bit. So, D0 to D3 and the other part is D4 to D7. So, I can say that this D0 to D3 value, so will be provided by this bank. So, I can connect this D0 to D3 here, and this D4 to D7 will be provided by this bank. So, I connect them here. Okay. So, these are the data lines for the memory chips and these are the address lines for the memory chip. These are the address lines. Now, but that is not sufficient, as I have said that if you put any address, so one location in each chip will get selected. That I do not want. I want that for a address range, first 2 kilo address range, that is from the address 0000 to say up to 2K, the first chip should be selected. So, if I am writing the address values as say A0, A1, A2, A10, then A11, A12, etc. Then, so from first, for the first all these values being zeros till all these values coming to 1. Okay. For this range, these first two blocks should be selected. For the next range, that is from this bit onwards, from this address onwards, that is A11 bit is 1 and these other bits are 0, A10 to A0 are 0 to this position. The second block should be selected, second pair should be selected. For the third what I, so for since now I need to access this third one, so I can say that as if for the A12 bit for these two are 0. Now, when the A12 bit also becomes 1, then when the A12 bit becomes 1, then this being 0, now it will be 0 0 onwards to 1 0 1 all 1, and finally for 1 1. So, this going from 0 to all 1. So, I can say that this range should work for the address value 0000, 0000, 0000, 0000, 0000, this 16 bit address. Okay. From there, so it should work up to say, so I am interested about the bits A11 and A12. So, this is 15, 14, 13, 12. So, this bit and this bit. So, these two bits I am interested in, this is A12, this is A11. So, from 0000 up to this 1111, the first bank should be selected. For the second bank, this A11 and this A12, so these two values should be 0, 1. Rest of the values remains unaltered. For the third bank, what I want is that this value, if this value is 1 and this value is 0, then the third bank should be selected. These values can be anything, and similarly for the fourth bank I want that this value and these both the values, they should be 1. These are don't cares, whatever it is. So, this is the range of addresses that has to be selected for different values of A11 and A12. So, that way the module should be selected. For that purpose, what we do, we put a decoder here. So, this is a 224 decoder. This is a 224 decoder. This decoder takes two inputs from the address line, which is A11 and A12. Okay. Now, okay, let us make okay. Now, so if it is let us say this is A12 and say this is A11. This is A11 and this is A12. Now, you see that it has, so this is a 224 decoder. So, it will have 4 output lines. So, this output line will be 1 when the both A11 and A12 are 0 0. So, this will be when these bits are 0 1, this will be selected when it is 1 0 and this will be selected when it is 1 1. Now, every memory chip has got one special control which is known as the chip select line. So, this chips it is, so this line is connected to the chip select signal of this memory block. Similarly, this is connected to the chip select block of the next memory block. So, this one is connected to the chip select of these two. This one is connected to the chip select of these two, and this one is connected to the chip select of these two. Now, what will happen? So, for this range of addresses, you see that this 224 decoder, it will output this value as 1 and this will be 0. As a result, these chips will not be selected, these lower chips, so they will not be selected. Whereas, for this higher value, for this A11, A12 being 0 0, so this chip select line will be 1. As a result, these blocks will be selected, and whenever whatever be the address coming from the processor, so the content of the corresponding locations from these two chips, so they will be available on the data bus, and those values will be coming to the CPU. Now, when the CPU generates an address beyond first 2 kilobyte, the next it is in the range of the second 2 kilobyte region. In that case, this chip select line will get selected, it will be output will be 1 and the others will be 0. So, this block these two blocks will get selected, and accordingly content of those memory locations, so they will come and they will be stored there. So, this way it will continue. Okay. So, this way if I have got less amount of memory, so it can be we can have this type of decoder incorporated into the system, and this incorporation of this decoder, so this will be helping us in realizing the less number of chips, less amount of memory. Okay. Now, you see that I have said something like I have said that the processor has got the address lines A0 to A15, and out of that I am ultimately in the previous example that I have considered. So, I can utilize the address line A0 to A12. So, if you look into the previous slide, previous page, so you see that we could realize we could utilize A0 to A10, A11 and A12. So, we could realize A11 up to A0 to A12. Now, what about the remaining bits? Like if I am writing like say bits like say A0, A1 in this way up to A11, A12, then A13, A14, A15. So, these 3 bits that I have, what happens to these bits? if the processor generates some address. So, you can understand that in this case, so we have not considered those bits A13, A14, A15 with the implicit understanding that the processor will always generate 0 for those address lines. But this is not correct, because the processor may generate some addresses in that range also, in which this A13, A14, A15 may be 0. For example, the processor may generate an address where say this bit is 0, this bit is 0, but this bit is 1, and these bits are all 0. These bits are all 0. So, this address, so where does this address get mapped? In the previous diagram, if you see this A11, A12, they are 0, 0, okay, and these bits are all 0. So, essentially in this diagram, so it will get mapped to this first block of first two blocks and the very first location of that block, okay, because it is all 0. So, 0, 0, A11, A12 being 0. So, this line, this select line is will be high. So, these two chips will be selected, and A0 to A10 being all 0. So, the very first location of these two chips. So, they will produce the output, and that will be available on the data bus line. Okay. So, that is what is happening. So, if this bit is 1, then it is actually the same memory is getting accessed compared to the case when this bit is 0. Similarly, whenever this A11, A12 is 0, 0, so whatever be the values of these 3 bits, so it will map to the same memory chip. Similarly, if this A11, A12, these two values become 0, 1, whatever be the values of these 3 bits, they will get mapped to the second memory block that we have got. So, this particular phenomena is known as memory folding. This is known as memory folding, that is the same memory location is being accessed because of by more than one address. So, I can say that this location, this 0, 0, 0, 0, all 0. So, this location is accessed by several addresses. How many addresses? So, it is accessed once here, once here, once here. So, every time it is accessed once, and how many such possibilities are there? So, since there are 3 bits, so with 3 bits I can have 8 different cases. Okay, I can have 8 different cases. So, there is a 8-fold folding. So, I can say in this particular design there is one 8-fold folding. Okay. So, this design that we have, so this gives us one 8-fold folding, because it is as if for 8 times the same memory location will be accessed, and that is quite natural. You see that individual memory chips, so they are 2 kilo, and if you multiply it by 8, so you get 16 kilo. And as I said that the CPU is generating 16-bit address bus. So, it is a 16 kilo address space, the CPU generates 16K address space, and out of which this individual chips being 2K in size. So, this covers the total of 16K. So, this concept is known as the memory folding. So, it may be good, may be bad. Okay. It is good because the programmer may not be concerned about whether using some larger memory space or not, larger address or not, which is beyond the given physical memory size. At the same time, it is bad because of the same reason that 2 different memory addresses generated by the processor, they are getting mapped onto the same address. So, as a result, it is the programmer may get confused. Okay. The same memory location may get modified by 2 different statements in a different fashion. So, can we stop this folding? Definitely we can stop it. So, we can say that this decoder, if we want to stop it, so what we can say that we want this all the 3 bits, that is A 13, 14, 15, all of them to be 0, then only we will be using this thing. So, if it is more than 0, if all these bits are not 0, then we can say that that is an address error or something like that. So, if you want to incorporate that idea, what you have to do is you have to just take some extra circuitry for solving this problem. So, what we do? We take one NOR gate, and this A13, A14 and A15 we put all of them here. So, this is A13, this is A14, this is A15. So, put them into a NOR gate, and this NOR gate output we so this NOR gate output will be 1 when all the bits are 1. So, this we can give it as a output enable line of this decoder. So, normally these decoders they have got an output enable line. So, that means if this output enable is 1, then only depending upon this A11, A12, this decoder will set one of these values to 1. If the output enable is 0, in that case it will be in a tri-state condition. So, all these outputs will be in a tri-state condition. So, this the decoder will not be able to generate any chip select line. So, all these lines will be in a floating state. So, none of the chips will get selected. So, by introducing this additional circuitry we can solve memory folding. So, whether we like it or not, so that depends on the system that we are considering.